Hello, we're back. Talk about some more moles. So as we were talking about moles and atoms and molecules yesterday, you might have been thinking to yourself, we don't really have anything that can measure moles. So how is this even going to help us to know that? Well, we're going to add another path onto our mole maps today because we're going to be talking about molar mass. In other words, the mass of 1 mole of a substance. When we're talking about the mass of a mole, we are talking about basically its atomic mass just expressed in grams. So if you remember on your big PT, back in the day when we were looking at what all of these numbers meant on the periodic table, the bottom number down here means atomic mass. Before, we were talking about atomic mass in AMUs, or atomic mass units. Well, it also means something else. It can also mean the number of grams for 1 mole of that element. Okay, so the molar mass is the mass of 1 mole of an element. It's found on the periodic table, and it's the number of grams in 1 mole. This can also be used as a conversion factor. 1 mole is equal to the number of grams. So we're going to be able to use that now to put it into terms that are actually useful for us in the lab. Because you're right, there really isn't anything in the lab for us to measure a mole with. Those balances, you can't put them in mole form, but you can put them in gram form. So if you take a look at your periodic table, some examples might be carbon. If you take a look at carbon, it has an atomic mass of 12.011. We usually just round these to the nearest tenth. So if we round that to the nearest tenth, 1 mole of carbon just weighs 12 grams. This is actually what the whole periodic table was based off of. They did ratios with carbon and what 1 mole of carbon weighed. 1 mole of oxygen, if you find that, has a molar mass of 15.999. Depending on the periodic table that you have, it could even have more decimal places than that. But again, we just use basically to the 10th, so we can round that to 1 mole of oxygen is 16 grams. If you take a look at hydrogen, 1.0079. So we can round that to 1 gram. 1 mole of hydrogen equals 1 gram. So remember what a mole is, 6.02 times 10 to the 23rd. That means 6.02 times 10 to the 23rd atoms of hydrogen weigh 1 gram. 6.02 times 10 to the 23rd atoms of oxygen weighs 16 grams, and so on. When you have diatomics, these are actually compounds. So we have to think of more than one of them. One of them weighs 35.5, 2 of them are going to weigh 2 times that. So the molar mass would be 71. Now we can pretty much do this with any compound, just like what we did with chlorine. So to get the molar mass, we just add up the molar mass of each individual element. So if we had SO2 for an example, sulfur is 32, and if we were to round to the nearest tenth, it'd actually be 32.1. Oxygen is 16, and we have 2 of them, so 2 times 16. So if we were to add up each of those elements, SO2 would weigh 64.1 grams per mole. So that means 6.02 times 10 to the 23rd molecules of SO2 equals 64.1 grams. That's ugly. 64.1 grams. 64.1 grams per mole. So, why don't you take a second, pause this video, and try a few of these examples. Take a look at your periodic table and see if you can find the molar mass of these elements and compounds. I'll wait. All right, I hope you got it. So for silver, all you have to do, it's an element, all you have to do is find it on the periodic table. If you find the silver on the periodic table, you'll see that it should be 107.9 grams per mole. Germanium, same thing, not geranium, germanium, same thing as silver. It's an element. So if you look at the periodic table and find it, it weighs 72.6 grams per mole. F2, this is a compound. So you have to look at fluorine individually, and then you'll have to multiply it by 2. So fluorine individually is 19. If we multiply that by 2, we get a molar mass of 38 grams per mole. NO3 has nitrogen, which is 14, and then we have 3 oxygens at 16 apiece. So if we add those all up, 62 grams per mole. H2O, hydrogen, weighs 1. We have 2 of them, plus our 1 oxygen, which is 16. You should have gotten 18 grams per mole. And finally, our sulfate ion here, SO4, sulfur is 32.1. Oxygen is 16, and we have 4 of them. So we get a total of 96.1 grams per mole. Again, it all comes from the big PT. All you gotta do is take each of them and add them up. So now let's actually use this mole to mass relationship to actually solve something. So if we wanted to know what the mass of 9.45 moles of aluminum oxide are, again, just like what we did before, we would start with what we know. We know we have 9.45 moles, and if we think about what aluminum oxide is, aluminum has a 3+ charge, oxygen has a 2- charge, so when those combine, Al2O3, so we have 9.45 moles of aluminum oxide, and we are trying to find the mass. So we need that conversion factor to get from moles to mass. Luckily, that's what our molar mass does. So our moles are going to go on bottom, our mass is going to go on top, and we know that for every 1 mole of aluminum oxide, we can look at the periodic table and solve for what our molar mass is, or our grams. So if we add up 2 aluminums and 3 oxygens, we end up with 102 grams of aluminum oxide. So our moles cancel out, we're left in grams, or our mass, which is what we wanted. So again, multiply across the top, divide across the bottom, and you would get 963.9 grams of aluminum oxide. Let's try another. This time, what is the mass in grams of 4.52 times 10 to the -3rd moles of C20H42? Well, again, we're looking for our mass. We are given moles, so start with what we know, 4.52 times 10 to the -3rd moles of C20H42. Moles are going to have to go on bottom, and we know that we can get to grams by using our molar mass. So 1 mole of our C20H42 is going to be equal to the number of grams based on the periodic table. So if we take 20 times our 12 plus 42 times 1, 12 is what 1 carbon is, 1 is what 1 hydrogen is, and we add that up, we get 282 grams as our molar mass. So that means there are 282 grams per 1 mole. Again, multiply across the top, divide across the bottom. Moles are canceled, we're in grams. So we would get 1.27 grams of C20H42. This time, we're looking for how many moles of iron 3 oxide in 92.2 grams. So this one is kind of backwards of what we've been doing. This time we're starting with 92.2 grams of iron 3 oxide. So Fe3+ oxygen is a 2-, so Fe2O3. So grams of Fe2O3. And this time we're going to moles. So we need our grams on bottom, moles on top. Again, for every 1 mole, we know that we can find our molar mass, or the number of grams, from the periodic table. So if we add up 2 irons, which is about 55.8, and 3 oxygens, which are 16, we add that up, you should get a molar mass of 159.6 grams per mole. Again, multiply across the top, divide across the bottom, and you would get 0.58 moles of Fe2O3. Again, this number right here just comes from adding these up from the periodic table. So, this leads us to a new path on our mole map. So we will add this in class today, but we know that we can get to atoms and molecules using 1 mole is equal to 6.02 times 10 to the 23rd, and we know that we can now get to grams using 1 mole is equal to our molar mass. This comes from our periodic table. But now that we have these two pathways, we can actually go one to the other. We don't have a pathway from atoms to grams or grams to atoms directly, but we can go through each other and use more than one conversion. So if I wanted to go from grams of something and figure out how many molecules, I could go grams to moles using my molar mass, and then moles to molecules using Avogadro's number. And vice versa, you can do the same thing. Each of these pathways is going to allow you to get from one thing to another using the conversions. So let's try one of these. If we want to know the number of grams in this many atoms of boron, we need to start out on our pathway at the atoms. Looking for my mole map. All right, found it. On my handy dandy mole map, we are starting in atoms, and we want to go to grams. So that means that we have to go atoms to moles, moles to grams. So if we start with our 3.7 times 10 to the 17th atoms, we know that there are 6.02 times 10 to the 23rd atoms in 1 mole. That cancels out our atoms. And now that we're in moles, to get from moles to mass, we need our molar mass. So moles this time are going to go on bottom. Mass, or our grams, are going to go on top. And we know that there is 1 mole for every 10.8 grams of boron. Again, this is just the molar mass, and it comes from the periodic table. So multiply across the top, divide across the bottom, you get 6.64 times 10 to the negative 6 grams of boron. Okay, so we just took where we were starting with, and we did both pathways together this time. You can go either way. We will be practicing this a little bit more in class. If you have any questions, again, feel free to come in and ask and get some extra help if you need it. Otherwise, I will see you next time. Signing off.